Alors, bienvenue à ce nouveau séminaire quantique Ivado. Je suis Luc Vinet, je suis le directeur général d'Ivado. Ivado, vous savez, je vous le rappelle, cette organisation qui a été mandatée par le truchement d'une grande compétition à réaliser ce qui est sans doute le plus grand projet en IA au Canada. Et pour nous, l'IA comprend le quantique, surtout dans son interface. Et Ivado couvre tout le spectre, vraiment, la recherche, et voilà, Gilles a toujours le mot à propos. Et tout le spectre, donc, la formation, la recherche, la mobilisation des connaissances, des activités scientifiques comme celle-ci, et puis aussi le transfert technologique. Alors, merci d'être là, de continuer à participer à cette série. Et encore une fois, j'espère que, bon, on a même des bonbons là, pour l'Halloween, c'est formidable. Alors, it's a great pleasure to have today Mio Murao. She is a professor from the prestigious Tokyo University. She's also the director of the head of the quantum. I don't know exactly. Okay, she's in charge of the compute quantum computing there. She has obtained her PhD from the Uchanomizu University. Is that correct? Yeah, I got it almost right. Um, and she's been a postdoc in Harvard, at Imperial College, and at Riken, also in Japan. One of her famous papers about quantum telecloning. She's a really major expert, a leading expert in quantum programming and algorithms, quantum learning, and distributed quantum computation. So she's exploring higher order quantum algorithms, and this will be the topic of our talk. So please welcome, and the floor is yours.
Thank you. So thank you very much, and it's a great honor to be here in this Halloween day. I saw several Halloween costumes, interesting, and then it's really nice. And then first view this beginning of this week was really nice, sunny days, and then I enjoy the blue sky and very beautiful skyline of Montreal. So today I would like to talk about these higher order quantum algorithms for learning quantum objects. And this is based on two talks on two papers. One is with Akihito Soeda and Satoshi Yoshida, and then another one is the Phil Taranto, Zen Rossi, and Ryota Roniwa. So the Phil is now working in Manchester. So I really wanted to go back in the very, very beginning, and then I mean, how humans are evolving and then with the finding new tools to play with. And then maybe the first human find out the fire, and then find the heat engine, electricity, electronics. Of course, the AI and the computer is here, and then we are discovering this quantum, right? And then I hope, and then I believe we are coming to the new era of quantum civilization. This quantum power somehow dramatically change our civilization as we have done in fire and steam engine and electricity. So we have quantum computer, quantum sensor, quantum control, quantum, of course, quantum crypto, and also all quantum thing. And then we are just arriving this stage. So we are not fully developed this quantum civilization, but it's a very good time to explore all the new things. And of course, this physics limit, a lot of physics limit what we can do. So we can't just do everything. But by full access, so this what quantum computer offer is we can now access all the quantum nature, all the quantum property, quantum world, whatever we can manipulate about the quantum world. We can use quantum computers. So before, this quantum world is always there. I think beginning of the universe, quantum is there, but we are not able to utilize too much. but our civilization, our is more like have a good more skill to exploit this quantum toward the really the edge of the this what whichever quantum can do. So yeah. So but we uh, we need to learn more. So with the quantum civilization, we need to learn more about quantum objects. But of course, um, understanding and then what I really would like to think about the next 10, 20 years or something, we would like to uh, extend our knowledge of physics into the normal physics is a physics given by the nature. But here is we can explore the physics of quantum programmable physics. So, for example, like teleportation started this like measurement, and then you do the measurement after the conditional operation, etc. We choose what to do, not the nature just give the Hamiltonian and run it as to the thermal equilibrium. That we can intervene, we can prepare, we can add more system and make entanglement. Also things we can do as long as quantum allows, right? So yeah, we can explore more on this kind of full accessibility to quantum. Maybe we can figure out something new in physics. So that's what we call quantum programmable physics. Another thing is like quantum computer is developing, and then but we don't know many good use of quantum computer yet. I guess, and maybe we hope it will be useful for drug delivery, etc., etc. But it's really difficult to provable advantage for the quantum computer. So we wanted to find the more things to the quantum computer can be useful, and then I hope this. As like a Feynman says, and like a learning quantum object with quantum computer may be helpful. Yes, please. Mhm. Right, right, right.
a, and a technological issue.
I think,
And I
yeah,
think if you were thinking about a technological issue here, but even if you implemented Shor's algorithm, it would not still not prove the advantage of quantum computers.
right, right, yeah. But we want to seek something at least under some good assumption, under good assumption, good assumption. Uh, it's better than classical or whichever. I mean, it's a little bit sad. I often do make up a nice quantum algorithm, and then look carefully. It's classically similarly doing well or something. So yeah, some of the problem this yeah, it's not that easy to figure out. Classical difficult, quantum easy problem is really difficult. But anyway, we need to challenge. So what we call quantum learning, people often misunderstanding quantum machine learning and quantum learning. These are slightly different. I define in a different way. But there's a this what do you target? What do you want to learn versus what kind of tool you want to learn? You want to use. So classical quantum target classical tool quantum. No, sorry, to quantum. That is maybe what quantum machine learning wanted to do, but you can do this. Given quantum system, you measure lots of data. This measure and get the collecting the data, and then processing every classical data about quantum thing. This is maybe another way of learning. But what I mean quantum learning, what I say fully quantum learning is we're our target to learn is quantum object, and we wanted to use a quantum computer to learn. So calculation has to be done all in quantum computer, and what we want to do is to do the measurement to get the classical output, or even we can get the quantum output. Quantum output means some state or operations, even the operation to get the output. So I think this is more chance to have quantum advantage because it's a quantum. Um, So we try to figure out this quantum learning in this sense. Yeah, this tells the like quantum object learning by given quantum objects, unknown object, and then you collect all the data about the quantum object and writing into the piece of paper in a classical thing, and then feed it into the classical computer and analyze it is usually difficult. But maybe we can hope everything in quantum. So this is just things. Yeah, so what I wanted to introduce is this fully quantum learning. We only don't want to get the unnecessary classical data out, but everything within quantum, and then you just quantum output, quantum input, yeah, but the full quantum. And here input can be state, or not necessarily just a state. It can be operation as an input. So this is what we are most interested in. Higher order is this map into the map of map. I will explain a little bit later. Yeah, so what we wanted to do this in fully quantum learning is of quantum object by quantum computers, and maybe for quantum application. Of course, we want it to be useful for humans, so don't exclude humans. Right. So, and then there are two types of quantum learning we can think of. One is basic quantum learning. Another one is advanced quantum learning. So what I call here is given, so here we kind of mainly learn about the maps. Maps as a state is a very special case of map we can consider. It's one kind of isometry is state. So just everything is a map in this world, just very extended way of thinking. But so basic task is estimating this unknown map. So in statistical sense of learning, like parameter estimation, these people are doing the learning means parameter estimation. But I think in machine learning sense, sort of mimicking the action is also learning. So regenerating this, so the usual machine learning, you don't really need to know the function, a detailed description of function, but you can apply that function. That is fine. That is your target. So regenerating a map, machine learning sense of learning. And then here I would say advanced task is not just learning map itself, but we wanted to apply some function of the map. That means you want to evaluate some number or some even some map onto your input map. So evaluation and generation of function of E. So to do this, you need to be on advanced, right? It's not just getting in and out, but you need to learn and then kind of applying it and then calculate it and then take it out like this. So what mainly we are talking today is like we wanted to consider this fully quantum learning with this advanced, most difficult type things. So example is unitary inversion. So I already using a lot of time in here, and then I need to go a bit quickly now. But in this talk, I would like to introduce what is higher order computation, and then for this learning sense. And then we have show two example, two different types of learning, quantum learning task. One is isometry adjointation, and another one is singular value transformation of unknown quantum channels. So we developed these algorithms. But after all, like what's quantum higher order quantum computation? And then to say what is higher order, we need to tell what's normal order. Normal order or lower order is a usual quantum computer. Quantum computer have a taking input state and output. Output can be measured, so you got some number, or you can speak out output state if you like for the future use if you like. So this what quantum computer can do is everything have to be a map, which have to be in quantum mechanics, you have to be a CPTP map for the deterministic operation. And then if you allow probabilistic operation, it can be instruments or POVM. So quantum computer, normal order quantum computer is quantum state processor. However, the higher order quantum computer is what is we take a map as the input, so function, this transformation as the input, and then we transform it to another transformation, so map to map. And this is sometimes we call supermap, and supermap is represented by a super operator. So super operator and super maps are different. Be careful. Yeah. Operator, super operator. Yeah. So this super map in general is represented by super operator. And then what the higher order is we use a quantum computer as a quantum processor. So not just state, but the process can be processed. And how to use and how to formulate, how to mathematically formulate this higher order quantum computation has been developed in under lots of different names. So Calgary group called Super Channel, Super Instruments, Pavia group say Quantum Supermap, Quantum Tester, Quantum Comms. A Vienna group said Process, Protest Metrics. This is lots of different names, but it's basically same thing. And then mathematical framework has been very nicely developed in 2008, 9, that kind of time by Pavia group. So what this map to map have to satisfy mathematically is if it's written in the Choi operator, some kind of Choi, the transformation of the map of map represented by Choi operator have to be positive, and then this, because this complete positivity has to be preserved. We have to map to map kind of thing. And then sort of deterministic map needs some kind of trace preserving property. And then very interesting thing is this is not a single operation, but there's a sort of a collection of operation to represent this super map, which requires some kind of causal order condition or signaling, non-signaling condition have to be introduced. So mathematically well defined. And the fun thing here is mathematically, you can consider lots of different causal ordering structure of what input map versus output map. And then input map can be used parallel, sequential, or dynamical ordering, or even the famous indefinite causal order. So you cannot order this, which one, the multiple operation, which one is before and after. Quantum switch, Lugano process, Grenoble process, lots of interesting, funny, higher order operation are known. And we are trying to do this something useful for this higher order computation, and then especially interested in the black box, this transformation of black box unitaries. There's a lots of list of black box unitary and how much. So replication is like a given black box to make a copying black box. And of course, as you expect, this no cloning theorem for this map also exists because this violates linearity. So such a, but if have a how many copy of you, how much we can close to the copy, these are also considered. So the lots of work has been considered. So most of these operation for this higher order operation is not done by single copy. So we need to have a multiple copies, so sort of a query complexity to implement this higher order quantum computation is kind of interesting and an important question. So one of the example is this unitary inversion. We have been working this for a long time, but the task is a given black box. You are allowed to access n times, and we wanted to implement this U inverse without knowing that. Okay, if you know, or if your unitary is given by circuit, you just run the circuit backwards. That's dagger, right? With the daggering everything. But if you don't know what it is, how to invert, which is not very obvious, right? So this is sort of like a given oracle access. You learn somehow what is L, not you, the quantum computer learn it, and then quantum computer invert it. So quantum computer generate the action of inverse. So it's sort of generative advanced quantum learning task. And this is just a rotation. So I would like to stress, if you know it, this inverse can be done by like e to minus iht, and h to minus h would give you an inverse. But if we don't know h, we cannot just put the minus sign on h. So we really need to transform t to minus t rather than h to minus h. So this universal unitary inversion actually implement negative time evolution. Actually, but time reversal evolution is different thing. So these physics people have to be careful. This and this are different. Right. Then then how to solve, of course. And then as I have told you, there's this nice formulation of all the possible supermap have to be decomposed into the circuit, which have to satisfy good relation. But it's a large space, too large space, and then it is almost impossible to optimize it. Of course, it's a huge dimensional space. Here we have a good symmetry. So we use, for example, this unitary inversion. There are two nice symmetry. This because it's if this has to be work universal, it have to put in some other unitary before and after, and then that would kind of, if that's also invert something, and then if you add this canceling this, this should also give a unitary inversion. So this means this quantum supermap, which invert U to U dagger, have this symmetric property, which implies this supermap is actually written in this joy operator have to commute with V tensor n plus 1, n minus 1, blah, blah, of these, this commutation relation really restrict our, what kind of operation it have to be. So yeah, we have some very good, I mean, it doesn't reduce to single one, but it's really reducing the search space dramatically. Anyway, so qubit case, we found a way how to invert unitary to minus arbitrary SU2 to this U to U dagger. And this was very surprised. We tried to prove this is not possible. We tried to prove no-go theorem, and at the end it's probability 1. So, and then we assume this is not possible. So what is the maximal possible probability to prove? And then, okay, this must be 0.887 or whichever we kind of expect, like something related to some cloning, etc. But then it's time to be probability 1. So you can do it. So this was very surprised. And first we found in the numerical, then my student, extremely Yoshida-san, good at group theory. He go very, very deep in group theory and figure out the correct circuit, which consists of like this Clebsch-Gordon transformation, and like this. So, but sad thing is it's not straightforward to extendable for qtrit or qdit case. So we don't know how it works in this kind of framework. Sorry? This is one qubit, unfortunately, yeah, one qubit operation. Yes, yes, yes. So, but for qubit operation, Chinese group has found another method to invert this U to U inverse using sort of global search-ish kind of algorithm. So that's what's great. So we now know every qubit, d-dimension SUD, there exists, I think, at the most order of d square query would allow to make it exact inverse, right? Yes, yes, yes. So we suspect d square, but the way based on the global search is more than that. Pi divided by 2 times d square. So slightly, but we know it is not tight. So still we are searching the optimal way. How do we do? Right. So what we know about it is like a U to U inverse or U transpose, U star. U star is actually easiest. That's kind of surprise, right? It's star transpose dagger is all related to each other. It can be this kind of operation can be the composite of other two, but somehow need a more query for inverse than transpose and then conjugation. So we developed this. Some of them are analytical result. Quite recently, we found this unitary to unitary transposition for Qtrit system. DGO3 is exactly done with 7 queries of unitary, which was also another surprise. We expected to be 6, but 6 didn't work. It's yeah. So it's always everything's always counterintuitive. This must be like that, and we try to prove it, and oh, it is not actually. But it's even more fun to see. So this is our most recent calculation. This is numerical calculation, transposition 7. Inverse must be more difficult. So I think we need this 9, but 9 we still not managed to calculate even using very fancy Clebsch-Gordon transform, etc. Sorry? Well, what is the size of the register? This is the number you mean. This is a probability. No, this is, sorry, fidelity. Sorry, fidelity. Okay. This is don't know this precision. It's a numerical, so it's we don't know. This is up to here is a correct. I think this is a floating point. Yeah. Sorry. Yeah. That's. So some of them are analytical results, so we don't have a floating point. Right. Okay. So, but then this takes so long, and then but now we wanted to think about this was like a one operation, U to U dagger. That can only do U to U dagger. But what we wanted to do is using such kind of transformation, and we kind of combine these together to build a new algorithm. So computation is something you can compose little elements to compose the program, right? So here we wanted to do this like this function of function, composing this function to build a new algorithm. Like the classically we have a like functional programming, everybody favorite, I guess, is the functional programming. Similarly, we wanted to do the map and super map, super map, blah, blah, blah. In this here hierarchy, we can build up a new algorithm. So ultimately, I'm really wanted to figure out this quantum functional programming, although it is still have a long way to go. We have been working on this quantum computation, so how to combine little parts of higher order operation to build up the somewhat useful algorithm. These are what we have, the list of what we have, and then today's sorry, this. Well, it's something wrong, but today we wanted to introduce one learning algorithm for non-unitary channels, because unitary transformation has been done a lot. So now it's a time for non-unitary. So I would like to briefly explain this isometry adjointation algorithm and this singular value transformation of unknown quantum channels. Right. So isometry adjointation. I think nobody knows what isometry adjointation is because this is made up words by us. So you don't need to worry. What is that? Never heard of. Yes. And so isometry is something like it's almost unitary. It's have a nice property of information preserving, but it is have a input, generally input and output dimensions are not the same. Okay. If it's the same, it's unitary. And then it's not reversible. So, and then like here is example, like one input 2, output 8, dimensional isometry, which is just encoding of like a simplest error correcting code kind of thing, right? You spread in quantum information into the larger space. And of course, you can always embed in a unitary, but if you cannot invert if the out the input state of input state output state is no, not output what you want to apply inversion is outside the range image of this the isometry. So so this make up task is if so given black box which implement isometry V from dimension from small d to large dimension d, we wanted to implement dagger. Dagger is well defined in some sense because it's a matrix dagger. It's easy to define. But if the input is in a right image, then it's invert back to original one. And if it's outside the image, it said, boo, boo, this is not the right one. So just checking it's outside the subspace. So this task does some kind of quantum learning, generative quantum learning task, where okay, here the given what you're given is the black box implementing isometry, and then also some unknown state. And then this isometry adjointation is a quantum learning of if the state is in the right image, and then it's gives the decode, automatically decode by just using forward this encoding, multiple use of encoding operation to decode, or if it's in the right subspace, just say it's wrong. So it's telling it's a subspace check. Okay, and important things here is this learning is done without revealing what the isometry operation is and the state are. So you don't know what they are, but you can check they are in the right subspace, or if it's in the right space, you can decode back to the original. So it's a nice task. And what we found here is not finding the good algorithm for isometry adjointation itself, but what we show is every isometry adjointation task can reduce to unitary inversion task. So instead of considering isometry adjointation, we can't just think about unitary inversion or plus a little bit of trick for measurement. So basically, nice thing here is isometry output is large D-dimensional space because it's mapped from small d to large D. And then this large D can be, for example, error correcting code case, it's an NQ-DIT space. So it's exponentially large than classicals. So if you wanted to kind of check what the state is, you have to do the tomography of this D to power N space, because which part of this big space its image of these isometries lives is not that obvious. But here, because we just can, this adjointation is reduced to this input unitary inversion, input side unitary inversion. We only need to do the invert small d-dimensional system. So that's very nice. Right. And yeah. So, but we don't know this everything about the unitary inversion. So That's a little bit of problem, but we are also building up that as well. Right. And how this works is we want this higher order operation that transform supermap to another supermap, right? So this is supermap, even higher than before, supermap. And then this supermap is actually nicely, you don't need to build up a new thing, but supermap is just a supermap. This is also proven by this paper. But nicely combining. So how to combine these with telling, so if you combine everything in a not nice way, you kind of close this slot. We have to keep the slot to transform supermap to supermap. If you close all the slot, the output is just a map. Okay, so nicely inserting other supermap, then we can transform supermap to another supermap. And here is a very nice thing where the again symmetry helps. Yeah. So this kind of supermap for transforming isometry to unitary have to have this weird what we call compression symmetry. So somehow the isometry spread your information, but somehow as a sequence, if we insert this red part, somehow it's give a compression to the small unitary, random unitary subspace. So this gives a very nice way to figure out what the supermap is. And there's sorry, okay, I skipped, but actually the circuit itself is given by a sequence of Clebsch-Golden transform as you expected. Because of this symmetry, you have this some kind of commutation relation have to be satisfied to make this isometry into unitary, and then then we can figure out this numerically how to obtain this what is the optimal fidelity or probability to transform isometry to unitary. So in this case, we for fun we try to do this. What are how the difference in the causal order of calling different black box matters, and somehow indefinite causal order mysteriously sometimes helps, sometimes not. We don't understand what's going on. Okay, so I need to quickly go to the next topics. So that was this more group theory main group theory is the main tool to analyze the supermap or supermap more efficiently. Here is another topics of which related to QSVT of unknown channels. So channels, as you know, it is a CPTP map, and then maybe lots of different representation. Cross representation is the usual stuff, but it'd be nice to characterize with Choi, Yamakowski representation, sometimes called Choi state, because, okay, it's depending on the definition. So here, if you use normalized version, this Choi state is a normal state. So it's sort of, I would call this is physical reality. Choi state is a physical reality. Yeah. So there's a map is if map is a physical black box is physical the reality, and then the choice state you can encode in a physical reality. But there is a Lubio representation. Another representation exists, and this is some metrics to characterize the map, CPTP map. Here is a weird thing. You have to do this reshuffling operation, which is not very physical. So mathematically you can do on the piece of paper, but you cannot implement in a quantum computer because it's not CP completely CP preserving map. It's sort of transpose related. I'm not quite sure now this Lubio represent is physical reality. Is that? Lorenzo might no can answer us, but yeah. So, but this one, this Liouville representation is it's a very nice representation on the piece of paper, because if it's applied to this vectorized state, like so, it is like the problem of dealing with channel. It is not just simple, like in the Krauss representation, it's represented by a set of operator, right? So it is not a simple one operator in Krauss operator. Choi case, it's turned into be one simple operator, so it's nice to handle. And Liouville operator, it's given by some metric. So it's a nice, very nice things to handle. And then mathematically on the piece of paper have a nice meaning. But quantum mechanically on quantum computer, we cannot really do anything, because it's not emission, and then not nice things. By the way, so nowadays this everybody, maybe many of you know, this quantum singular value transformation is very popular to view many algorithm, and then sort of encoding any metrics into the part of unitary. Then you do this polynomial transformation to do the singular value transformation. These are well very actively researched. So we want to do here, so we want to apply QSBT technique to channels. Channels itself is not the easy things, because it's not just simple metrics, right? But we wanted to use this Liouville representation to learn. So the target, we want to learn some nonlinear property of quantum channel. And then we hope this QSBT, you can calculate such a quantity. The big problem is how to block encode. And then lots of block encoding people give this weird access of Krauss operator is known. Steinspring is given, etc. So it is not a black box. You need to know quite a lot about it to specify Steinspring or Krauss operator. So, but because we wanted to use this for a learning algorithm, if we know everything, it's not the point. so we wanted to know. We want to evaluate quantum. We want to do the quantum learning for black box quantum channel. So how do we do the block encoding of this quantum channel? And then what kind of property of channel we want to learn? Maybe we wanted to learn eigenvalue and singular value of the channel, right? This is maybe first suspect to learn about it. And okay, then this Liouville representation, which doesn't have a very, it's an unphysical object, but it have a very nice meaning in terms of eigenvalue and then singular value. And if you don't know much about the Liouville representation, it's a vectorized the action of your map on a vectorized space. The best thing of the Liouville operation is like it's concatenation of these metrics represent this concatenation of the map. So unitary case, it's work like that, but Krauss operator, you don't concatenate, right? This to represent a whole map. So this is a very nice property of Liouville representation. And look at this in this double vector representation, this Liouville representation. Eigenvalue, singular values are really naturally that eigenvalue and singular value of Liouville representation. So it's just working on this, we can figure out this eigenvalue and singular value representation. But as I tell you before, this the reshuffling one would give the choice state. Choice state is a nice state. We can prepare as it is, but this so choice state, what is sometimes called Choi B operator. That's why we put EB. And this Liouville operator representation is sometimes called Choi A. So then we put the EA. So EA is our Liouville representation. And then, yeah, right. Then, but the big question is, okay, this is unphysical object, but do we want it to encode, block encode in a circuit, this physical object? How do we do? So we actually find a way, and then there is a good way how to block encode. But first you have to elmitize. Elmitize means this making of this off-diagonal block to put this. But this can be encoded in a unitary, in some nice order of, yeah, it's maybe not nice because it's you look this d to power 2 to power k plus 1. This might be big thing, right? So these are the necessary query. So it's a dimension to the power k. K is some number related query you need. So it is not cheap, but we can do how it is. So the circuit itself is quite simple in some sense. So we apply this map onto our maximally entangled state, and then do a control swap. And in this control line, we have to prepare this 0 and 1 superposition. So you make a superposed sort of choice state. And then we do this apply partially transpose exponentiation. So we wanted to exponentiate this rho into this some on the shoulder of exponential, which can be done with this partial transpose operation. And then once it's on top of the exponential, we wanted log to make block encoding. So this can be, this circuit doesn't like obvious how why it works like that, but if you have some nice diagrammatic representation, it's how this is possible is sort of very clearly seen. Right. So now we have exponentiating this Rubio operator, and then QSVT to take a log. We can encode, block encode this Rubio representation. Okay, so and then we can show some lower bound. So this is like if this block encoding can be done in some small number of oracle call, then it's allows this unitary discrimination, which cannot be done, must not be done with small number of query. So that gives a lower bound. But lower bound already require D dimension dependent query. So block encoding of this Liouville representation for arbitrary unknown channel is actually lower bounded. This query complexity is lower bounded by D. So it's not easy. I hope this can be done like without dimensional coefficient. Then quantum computer will be really nice things to analyze all the channel. But yeah, this dimension depends. This Karstoff dimension is here. So that's a bit disappointing. But at the end, then we can calculate, for example, the singular value moments, the sum of the power of a singular value can be obtained by running this kind of standard swap circuit to obtain. Right, okay, so I think we are almost done. Yeah, and then this we kind of compare to the more straightforward way. If it's a more higher moment, our method is doing somewhat better. So at the end, the recap, like what was quantum learning, and then what's the basic and advanced quantum learning, and then what we wanted to do this fully quantum learning. We wanted to evaluate the channels, the isometry version, we wanted to kind of invert or checking a subspace, that's a generation, or the Liouville representation part, we want to evaluate the singular value moment, etc., by just applying a quantum computer. This our measurement is really toward the end. So what we can do, And then this is all we use this utilizing higher order quantum computation. So we use this oracle call, and then what kind of operation we can insert between this oracle call. So in physics, I think in a normal physics system, you can apply, somehow you can connect your physical system to environment or other system. This is also already kind of inserting supermap, or applying pulse is shining the laser in a right way in a nicely programmed method. That is also representing supermaps. So I think this is not just like a cartoon, but we can do in physical, real physics to implement this higher order operation. And what we found, is we show as two types of quantum learning, fully higher order quantum learning algorithm. One is isometry adjointation, which utilizing nice symmetry property of the supermap supposed to satisfy. And somehow this isometry adjointation can be reduced to unitary inversion. And the other one is singular value transformation, which like a channel is something not the metrics to start with, but somehow we write a nice description of metrics, which is nice but not physical one, to now map to physical one. Then on top of the physical, once it's in a physical reality, somehow we can process inside the quantum computer to calculate the value without without classical computer, right? If we wanted to do classical computer, you need a lot of memory space to keep all the data. Then you do this diagonalization or whichever lots of calculation. But in here, everything is done in unitary, and then in quantum computer as a unitary operation. So it's fully quantum calculation of learn things. We can do this kind of thing. So yes, so that's all. And then thank you very much for your attention.
Thank you very much. Are there questions? Well, yeah. Can count on you.
Hello, you hear me? So thank you for your talk. It was very nice. I think one needs higher order thinking to assimilate everything, but it's very rich. I have a naive question first. So can you explain what you mean by the nonlinear part of a quantum channel? It's linear under mixing, but
No, nonlinear part of quantum channel. You mean the nonlinear transformation done by singular value transformation, this part?
yes, at some point you said you wanted to quantify the nonlinear part of a quantum channel.
So everything quantum channels linear, of course, and then we wanted to transform into the other form. That's fine, and then we block encode. And here this transformation we apply to calculate singular moment. This is nonlinear, right?
Yes.
Yeah. So this is the power of QSBT we can do with without QSBT. We can still do some evaluating some linear things, but yeah. So here is a the choice of this F is and then you have to do the block encode this FH into here to evaluate this, which maybe in practice may be difficult in experiment, but yeah.
Okay, I see. So just
Okay.
the moments of this linear object.
Mhm.
And the second question, very fast, is in the first part, you use SDP to establish minimum number of calls to establish inversion,
Right.
for example. As you grow to Hilbert space, SDP diverges exponentially, and so you have to use other tools.
Super exponentially.
And so do you have other optimization tools that you're using?
So,
That's a numerical
so
distance.
therefore, this group theory helps. So we reduce the parameter dramatically with this group theory. Do you see this?
And so you can always map it to an SDP with the symmetries that remove.
Of course, with dimension, it grows. So we can only manage to calculate 7 or something, and yeah. So I mean, it's never been constant. So it's this 7. 7 is the largest. 7 slot comb is the largest thing for Qtrit we can do now. So it's not a solution in some sense, but just not running a SDP, but using a good basis where you have a much smaller number of parameter, that would work better. I mean, it's not solve all the question. Yeah. So this paper tell how many originary parameter we have, and then this group theoretical analysis, how much we can shrink this parameter space. So yeah, maybe please check.
Thanks.
Yeah.
Thank you for the really nice presentation. I'm a bit shocked, however, as far as I'm concerned, I've never seen a closed quantum system. I'm part of the universe and I interact with open quantum systems as I'm one all the time. And to me, the Liouville representation is by far the most physical one to talk about decoherence, or, you know, in nonlinear spectroscopy, you name it. But I'd like to understand why, from your perspective, would a choice state be a more physically realistic representation?
Yeah, but using this block encoding, we can directly encode this Liouville representation in a circuit. So that's good.
So it's from the perspective of representing it as a quantum circuit.
Right. Because what quantum computer can do is only run in a quantum circuit, right? Basically. So we need to somehow encode into quantum circuit what you want.
Okay. Yeah. They're very artificial systems, though, quantum computers.
Yes, that's right. Yeah, that's right. But a quantum computer is made of physical systems. So in the real baseline, it's run by Hamiltonian, right? But the important thing is switch on and off and on and off and on and off. This very controlled, time-controlled sequence of a Hamiltonian. Mm-hmm.
Hi, thank you for the really nice talk. So far you have developed learning algorithm to learn complete unknown unitaries, right? Do you know if you still have some information about your unitaries? For instance, if you have some kind of crystal exhibiting translation symmetry, there's a lot of structure here. Do you know if this kind of symmetries or knowledge on your unitaries can give you much more power?
Right. Yes. I mean, if you're maybe not the SU2, but SO something, so the restricting to real unitaries, we can do a little bit better than that. There exists some nicer algorithm for utilizing what you have known, and this is really interesting. What kind of knowledge would give you the problem much easier, right? How this little bit of knowledge would reduce the complexity, the oracle complexity. Another interesting question is this knowledge. Is that knowledge have to be classical knowledge about something? And what we recently working on is we can consider quantum knowledge of quantum things. Which, for example, I give you an eigenstate of this unitary. I don't tell you, but I give you. You can access to the eigenstate. This is sort of I give you quantum knowledge, or knowledge encoded in quantum. But of course, to learn this what the state is, you need a many copy to do the tomography, right? So you don't know it, but you have it, quantum object. How much this would increase this like a other resource to solve the question easier or not? This is a very interesting question. I wonder what this kind of knowledge is reality or not, or this always fun question. Yeah.
But there are situations where you can solve an inverse spectral problems without having to get too much knowledge on the states. So you can, in some situation, it's interesting to ask the conditions under which this can happen. But if you know the spectrum of a problem,
Mhm.
you can work out what the Hamiltonian, what the unitary is. So there are, I know some cases where you can do that.
Yeah, so one of the interesting example of this quantum knowledge of unitary helps is controlization. So transforming unitary to control unitary is not allowed. It's no-go theorem in general. But if you don't know, but if you have one eigenstate, you can controlize. This is yeah. So somehow, yeah, there's some non-linear transformation is done by having this access to the one eigenstate. So yeah, it's still mystery what's going on.
Or you had a question. You kindly.
Thank
Sorry,
you.
yeah.
Thank you. Thank you for the answer.
Something.
No, that's okay. Thank you.
Okay, perfect. I'm sorry for this maybe naive question for someone has not been for so long in the field, but once you learn the the inverse or the isometry you want, what do you do with it? Is it stored in some kind of quantum memory and then reused as some quantum knowledge, or is it decoded into some classical data and then reused later? What happens once you learn it?
So you just keep it. You don't learn anything about. So you can invert it, but you don't know what it is.
So, okay, so you just, in a black box fashion, you have to reuse it right after that.
Yes. Okay. There is one trick you can do: store and retrieve. You can choose input state later, which is another trick exists.
Mm.
So yeah, I mean reducing success probability, but yeah, you just invert the action, but not applying to the state. That is also possible.
So there's some kind of quantum memory happening here.
In that case, you store your action of the inverse into the state, which is called the store and retrieve, or quantum programmable processor. There's lots of fancy name, different name. Yeah.
Thank you.
So there are some schemes as what you want to do. Yeah. So
Okay.
with the memory.
Thank you.
Oops. This role is very active.
Yes, thanks for the talk. Maybe I'll ask lower order problems. So, so for like it's really interesting you give those notation on quantum learning. So I have a question: is that if you have access, so if you have a state that you want to do some perform some unitary, or like in my mind I was thinking of dynamics. So to another state, and you can increase the states, you can get sample from these states. So can you using like maybe like if you somehow you can parameterize those like the Hamiltonian of the unitary, like, or the generator of Hamiltonians of the unitaries, you parameterize by neural networks or classical learners. You're using those classic samples to learn for those dynamics. Would those implies that for those the final states you got is like you can get it's classical simulatable or like something.
Classically simulatable. Okay. So there are some other group in this how the classically like we don't require the real map to be implemented, but maybe we only evaluate some observable expectation of the observable. So this is called the virtual COM or virtual supermaps. which if you only wanted to care about the expectation value, there is a easier way. So these are sort of sampled, and then you kind of calculate the average. Yeah, and in that case, this we don't need to implement completely positive map, because you this like a classical shadow, or like you just calculate each instance and then plus and minus to average over value. So yeah, such a thing is also like a higher order, but the virtual version, if you only care about expectation values.
So if I care about, for example, if I want to prepare quantum states by using those dynamics, so with those quantum states, you can easily prepare.
But you want a state.
Yes.
State case, you cannot use the virtual. But if you wanted to measure some observable of the state, then you can do this virtual trick. Yeah, but preparing state is not possible in that way. Yeah.
Thanks.
Thank you very much for the talk. I have a probably naive question. Here, when you were explaining like calculating the U-inverse, you were talking about querying the function, the black box function U that we don't know what it is. Does it mean evaluating it on a set of input, and are they chosen randomly? So querying means querying on random input points?
Query means you apply unitary. So you can choose your input state and apply. I mean, it's not the input state, but it's a part of the circuit. So it's a number of the core you need to implement. Yes, so yes, I agree. There's actually, for the people from the machine learning, this learning is it's one kind of yeah, not obvious. Maybe it's I mean, should we call this learning, right? It's just not learning, but just running the function. So it's a sort of oracle learning scheme, but it's a bit different from machine learning that. And then somehow I kind of make a confusing it's fundraising people can can confuse and give me money or for this learning more thing. I don't know, but yeah, but this is kind of quantum learning. It's not the same of the usual learning. So that have to be, yeah, slight. Yeah, it's a good point, I think.
Okay, thank you very much. Thanks.
Yeah.
Okay. No more questions? Well, let's us thank one more time.
Thank you. Thank you very much.